He's probably right.
Okay.
What does that mean? Equal and opposite of force opposed.
So here's a couple of things that happen. So we have Mr. Elliott is here. Mr. Elliott was in high school back when I started teaching here in 1993. You graduated in what, 94?
95.
95. So he would have been, he's been here. I've been here. Anyway, so he journeyed away and he came back, and now he's back in his high school as an assistant principal here. And so I invited him to come down and watch the, sort of like a rite of passage when we get new administration. They need to come down and watch the breaking of the block on the bed of nails. And so also joining us, hopefully, is the new superintendent, Dr. Greer. So we've invited her, so she's supposed to be here as well. So we'll have a couple of esteemed guests here to watch me potentially die. So,
One esteemed guest.
well, let's go with two. I think we can call you esteemed. Okay.
Very nice.
All right. So, are we going?
Yep, I already started it,
Okay,
actually.
fantastic. Okay. So here's what's going to happen. Well, I'll wait till Dr. Vick gets here and she can hear the his explanation. So let's talk about the lab from yesterday, okay? So there's three distinct parts to the lab. So the first part that happened is that you had a block of wood, and the whole key to this is that you hold it at a constant velocity, okay? So if something's at a constant velocity, what do all the forces add up to? Zero. So you had four forces. You had your force applied, you had the force to overcome the frictional mafia, you have gravity, and you have your normal force. Now, how did you all measure the gravitational force acting on the block? What did you do?
Math times.
No, you didn't.
No, wait, no. Oh, we did that thing.
You took a scale, right? You held it up and you said, oh, it was 3.90 newtons. Okay? That's what you did. So that's the simplest way to calculate the weight of an object. Take a Newton scale, hold it up, boom, there you go. No calculations to do. Do not multiply by 9.8 meters per second squared. Do not pass go. Do not collect $200. Okay? Just get the reading on the scale. Oh, we got media here. Oh, great.
Wow, you're
Great.
famous.
No, I know about that. So, because of the fact that you'll be talking about the sum of the vectors, we're going to make that a negative value, okay? So, wow.
Why do you have an audience?
That's Dr. Greer's coming over for the...
What are we doing?
What do you mean for what?
The nails.
Just wondering.
What nail thing?
You know,
It's right there.
You light yourself on fire.
no, it's just the old bed of nails. What? You disappointed? You want fire?
You lit my head on fire on the in-service day.
Ooh.
Not really.
Really,
Okay.
Mr.
Anyway.
Finger burn.
So dramatic. Okay, so you got a negative 3.9. So what keeps that block from falling towards the center of the earth?
Force normal.
Normal, right at the table, right? So that's going to be, do not make this difficult, do not make it complicated. It's just going to be the opposite of your gravitational force. Okay, that's it. Now, you measured the applied force, which I'm guessing might have been something around 0.90 newtons. Okay, pretty small amount of force. Okay, so that's what you have to pay the frictional mafia. Okay, because the frictional mafia comes along and says, "You want to move? Hey, you're a good boy. You got to give us some. You got to give us some money." So that's what you have to pay the frictional mafia. So that's going to be negative 0.90 newtons. So you add them all up. What do you get, Preston? Zero. Said absolutely no confidence whatsoever. You get zero. So when all the forces add up equal to zero, one of two things could happen. It could be at rest, or it could be moving with a constant velocity, but it's not accelerating. Okay? So you're going to draw a vector diagram using that as a free body diagram. That's what it's going to look like. It should look like a big plus sign. Okay? Show me the scale. Did you let 1 centimeter equal a Newton? Did you let 2 centimeters equal a Newton? Okay? That's what you want to look for. Now, then you're going to draw that tip to tail. I always draw gravity first, then like my force applied, then my normal force, then my force friction. You should end up back at the origin. And the reason that you end up back at the origin is because you're in equilibrium. You're at a constant velocity. The sum of the forces is 0. What are you doing?
One of the phones is playing music.
I just couldn't figure out what you were doing.
Can you hear me? Okay, they're not crazy.
Okay.
Okay, it's playing music, it's playing music.
Find out whose phone is playing music for the love of
See, now
all.
he's got it.
Oh my god, please don't be my phone. That would be so embarrassing.
Hey, I'll go.
Check the 28 real quick.
Did you know?
What is 1.4?
No.
Okay, good. It's not mine.
Why is it you?
You want me to leave now?
No, we're good. It stopped? Okay.
Yeah.
Okay. So,
Sorry I let her in.
that's okay. So, a Corgi fan, really. So, that's one way to calculate the frictional force. Figure out how much force it takes to pull it. That's how much frictional force there is opposing it. Okay? Got that idea? Fantastic. All right. When you get down to those questions on the bottom of page 1, okay, do not make this complicated. So you're going to try, down there on number 6, you got a car with a mass of 1,000 kilograms, okay? So the car is moving along. It's like me taking this and I push it. Why does this thing come to a stop? There's friction, right? So here's the car. There's 3 forces acting on the car. What's one of them? Gravity. What's another one?
Normal.
Normal. Now, if the car is going in this direction, what's the third force?
Apply.
Friction.
Oh.
Okay?
What?
That's it. Okay? There's no other forces. There's no force pushing it. Do not confuse inertia as a force. Inertia is just the tendency of that car to keep moving at a constant speed. Okay? So at this point, you have 3 forces. Are they going to add up to 0? No. So what's the car going to do? Accelerate. Okay? Now, think this through. The car is moving with a positive velocity of 10 meters per second. You hit the brakes. What's the car going to do? It's going to stop. Is it going to accelerate?
Wait, yeah.
Yes, it's going to accelerate, which means the forces don't add up to 0. Okay, so I've got a gravitational force, I've got a normal force, I have a force friction. They do not add up to equal to 0. The car begins to accelerate. Now, you have a positive velocity. Fisher,
Yes.
you have a positive velocity.
Tough.
Got it?
Yep.
You're going to stop.
Tough.
What's the sign of the acceleration?
The sign of the on like when stopping.
Yes.
Negative.
Why?
Because you're
right.
because you're slowing down.
And they have to have?
Opposite signs.
Fantastic. Okay. So, F equals MA. Maggie, F equals MA. True?
Yeah.
Big sign right above your head.
Yeah.
Is mass ever negative?
No.
No. Scalar quantity. Fisher says I have to have a negative acceleration. And he's right. So if I have a positive mass multiplied by negative acceleration, I have to have a positive or negative force.
Negative.
Fantastic. So I know the force that's going to make this car stop has to be a negative value because I have positive velocity and I'm slowing down. Now here's the problem. You have an absolute value of mu times force normal equaling force friction. These are absolute values. So what you do is you find the force friction and then you decide in the context of the problem, do I make it positive or negative? Now at this point you're going, I've got mu, I gave you that, 0.7. Okay, you have that number. Don't have to do anything with it. But you don't know what the normal force is. But you know that the normal force is the same as your gravitational force. And how do you calculate your gravitational force? mg. You know the mass of the car. Yes. Do you know the acceleration due to gravity? Yes. So you can find the weight of the car. If you find the weight of the car, you know the normal force. Multiply those two together. Multiply that by mu. Okay? Now, that's an absolute value. You get the number. Okay? Then you decide if you make it positive or negative, depending upon the situation. So the only thing that changes in the next problem is that I give you a higher coefficient of friction. Still the same car, still the same velocity. There you go. So make sure that those answers are negative. Now, they don't come out negative mathematically, but you have to decide in the context of the problem, does it make sense to make that force friction be a negative value? Okay? Cool with that? Yes. Because you have positive velocity and you're finding the frictional force. Okay? Now, when you get to question number 9, okay, the first thing you need to do is calculate the acceleration of the car. You don't have time, so what are you going to use? You're going to use that equation. You're going to use that equation and you're going to find the acceleration. Your acceleration should be, and this is an ish, okay, should be around -5, -6 meters per second squared. Okay? That's what you should get as your acceleration, which for a car is a pretty decent acceleration. And like you'd have to hit the brakes pretty hard to make that happen. Now, do not make your frictional force calculation difficult. Frictional force also equals mass times acceleration. You know the mass of the car. You know the acceleration that it caused. Multiply the two numbers together. Okay? That's all you have to do. Do not make this difficult. Okay? So that should be around -5,000 newtons. Okay? You're stopping a pretty big car with a pretty good acceleration. So that's a pretty big force. Okay? Now, when you calculate mu, there's two ways you can do this depending upon how you want to do the math. Okay? So, mu is force friction over force normal. You just found the frictional force, but remember this is an absolute value. So one option is that you go, oh, force normal is the same as mg. Force friction is mass times acceleration. So here's the two things that you can do depending upon the voodoo that you want to do. One option is that you can look at this and go, this is why you work with variables, you can go, oh, the masses cancel out. It's a ratio of your acceleration. So one option is that you take that acceleration that you found first and divide that by 9.8 meters per second squared. One option, okay? If you don't like multiplying by mass, it's just a ratio of your accelerations. Now if you go, oh, Mr. Burkamp, I'm a purist. I want to do forces. Okay. Take that answer that you found for your force friction, take the mass of the car and multiply that by 9.8 meters per second squared, get your normal force, and then divide the actual forces. Okay? So it's either a ratio of your accelerations or a ratio of your forces. Okay? Your answer to number 10 would make a horrible GPA. Okay? A horrible GPA. Make sure on that force table that you have 3 diagrams. One is going to be that tipped or as a free body diagram, and the other one's going to look something like that. Okay? And then on your graph, which is the 5th thing you should have, that should look something like this. Make sure that you have circled the points on your line of best fit, and you have shown me how you calculated that slope. We're good. Yes, ma'am.
How do you do number 5 on station 2? What?
What do you mean?
I don't know how to answer. Like, you just say that there's no result because you're reaching equilibrium?
Yeah, because it's not accelerated.
Oh, okay.
Yeah, do not make that too
okay.
complicated. Eli.
Number 11 confused me. The 3 ways to determine the force friction. Do you just like want equations or?
Okay, there's two. Okay, start at the beginning of the lab. you took the scale and you pulled it. How did you use that scale to determine the force friction?
Well, it's the opposite.
Okay, that's number one.
Wait, no, I have that. Never mind, we're good. No, I didn't write like a scale though. I just said it's. I'll just write. Okay.
UMG. Okay? UMG. Now, how did you calculate the frictional force on number 7?
I use the force friction equals mu times.
Okay?
Is that?
That's
is it-
number 2.
Is that different?
Then what?
The first one.
Yeah, the first one, you're just measuring the
Oh,
force.
just like with a scale.
Yeah.
Okay.
Now, how did you find it on number 9? It's a big sign hanging hanging up above Maggie's head.
That's your exam, right? Okay, cool.
So you can pull it, mu times force normal, MA.
Okay.
Got it?
Yep.
Okay. It's like we're waiting on the president. Yes?
You might want to check your email.
Did she email him? Did she?
Yeah, did you have that?
How disappointing.
Yeah.
Oh my goodness.
Equilibrium and there's no acceleration.
Oh, okay. We don't have to wait on.
Just right
Okay.
there in front of me. Anytime I look at the board, I'm looking at the email. I feel so bad, but I just saw it, so I was like,
Yeah.
say something.
Okay. So Dr. Greer is not going to be joining us, which means you get to drop the hammer. Okay. So here's the no. We didn't explain it first.
Oh.
Literally, it's the hammer.
Why do you do this?
So here's what's going to happen.
Oh.
In the back, there is a bed of nails. Get this picture off. Oh.
Give me that stapler.
Yeah.
After.
Yes. So here's what's going to happen. I'm going to lay on the bed of nails.
Oh.
And then we're going to take a concrete block, and we're going to lay the concrete block on top of my chest. Okay?
What?
At that point, Mr. Elliott is going to take a sledgehammer and he's going to smash the concrete block while I lay on the bed of nails as the concrete block lays on my chest. Okay? At this point, everybody goes, "Ooh, that's not going to end well." And it might not. Okay? There's always that risk that it doesn't end well. So far, we've been okay for the most part. So, but what I'm going to place my faith in is in the 3 laws of motion. Okay? So what's Newton's first law of motion?
An object is in motion will no. An object in motion will stay in motion unless
Okay.
another force is applied to it.
Law of inertia, right? So I have mass, right? Okay? The block has mass. The sledgehammer has mass. So the sledgehammer is going to come down, right? And it's going to be moving, and it wants to keep moving until a force acts upon it, right? So hopefully the concrete block provides a force, right? So the only thing that affects inertia is mass. So I have a relatively large amount of mass relative to the sledgehammer and the concrete block, okay? So hopefully with that, by taking advantage of the fact that I do have mass, hopefully my body says, we're really not going to accelerate very much today, okay? So then we're going to look at the second law. Force equals mass times acceleration. So hopefully I have, again, a relatively large mass. So I don't want to accelerate very much, because if I do accelerate a lot, bad things are going to happen, okay? Someone's going to call a nurse Dana, she's going to come down with ice chips and crackers, okay? Now, the whole key to this is actually Newton's third law. Newton's third law says forces are coupled. For every action, there is a reaction. So if we define down as being negative, so Mr. Elliott is going to hit that block with a negative force, right? So by Newton's third law, what is the block and my body going to do? It's going to exert an upward force, right?
Yeah.
Now, hopefully, and these are Newton's third laws, These aren't Newton's suggestions, okay? That's going to be a positive force. Now, here's the whole crux of this. Force equals mass times acceleration. Now think this through. When Mr. Elliott hits that hammer, and that hits my block, do I want the hammer to accelerate? Yes.
Yeah.
I want it to accelerate. Because if it doesn't accelerate, what's going to happen?
Goes right through.
Yes, it's going to maintain a constant velocity and go straight through my chest. Okay?
Oh.
That's not going to end well. Okay? So I want that hammer to accelerate. True? But what do I want that acceleration to make it do?
Break the block.
Break the block, and more importantly, I want it to slow down. Okay? I want that to slow down. Now, if you look at this in terms of F equals ma, the sledgehammer has a relatively small value of mass. Okay? So I want it to actually have a big acceleration. I'm going to have a relatively large value of mass, so I want to have a small acceleration. I don't want accelerations to be equal and opposite. If accelerations are equal and opposite, this is not going to end well for me. Okay? Got the idea?
Yes.
Okay. Let's go.
I want my. Wait, someone. Gracie, get your phone and send me the video.
Get your phone.
No, I have to video it. So wait, is there a reason you're on a bed of nails, or is it just for kicks and giggles?
It's just for dramatic flair.
Okay.
Yeah. Okay. Actually, stand up here. I need you to help me, like, lay down.
This is all going on YouTube. I'm nervous. I'm nervous as well.
What if you like misses and just hits your Can I get a picture of you at 0.5?
There we go.
All right, so take the block. Or I will, but let's get the block on first. Yeah, that's a key component of the story. So lay it flat this way. There you go.
Can I video at 0.5? Oh my god.
Yeah, you can.
Okay.
You look good over there.
All right, so he's going to come down
Should I?
applying a negative force. The block should provide an upward force.
Sorry, guys.
That should accelerate. Now, yeah, use the low end. Okay? Yeah, not the sharp end.
Okay.
Now, you're not trying to ring the bell at the carnival,
Okay.
but you can do like a good half to 3/4.
Oh my god, I'm scared.
Okay, I actually want you to hit it hard enough that it shatters. Because, yeah, because if it doesn't shatter, then all of that energy gets pushed in my chest. So I want it to shatter and take some of that.
Should I record this in slow-mo?
Yeah, no, you want to get it right here on the center of that bridge.
0.5 slow-mo.
You want to hit that and then it should shatter.
Pretty hard.
Okay, so do that.
Yes.
Oh my god.
I'm trying to talk with an elephant on my chest. Okay.
I need goggles.
No, you're okay. All right, you ready? No pressure.
I'm worried.
Oh, you shouldn't be. You're worried.
I'm worried.
Okay, I'm not. You ready?
How hard?
Literally, like a good half to 3/4
All right.
Okay?
Oh god.
You ready?
Ready?
Yep.
Countdown.
3, 2, 1.
Whoa! Are you okay?
This is under the center.
Oh my god.
Is that too hard?
No, it was good. No, it did exactly what it was supposed to do.
What the heck?
Okay. Okay.
No more physics class.
Yeah, that was a good shattering. Okay.
I got it in slow-mo. You want to watch it?
I do.
Wow. Oh, he hit you in the stomach too after.
did.
Ouch.
That was good.
Oh, yeah. All right. I'm good. Yeah. No, it was good.
Did I get him in the stomach?
Oh, it's fine.
Yeah.
He's okay.
No, I didn't. If you did, I didn't see it. Okay. No, we're good. Yeah, well, yeah. We're good. Yeah. Keep that. Okay. All right.
Wow. Close up.
Okay. Okay, well, here. Come over here.
Oh, okay.
Come on back here. Okay.
Maybe it's not real, you know? It is.
Okay. You ready for the physics lesson? Okay. So I've got yonder balloon. And put on tape. Okay. Here. Now, when I let go, what should happen? Is it going to accelerate?
Yes.
Yes. Which means there is a force. So which direction should it go?
That way.
That way. Why?
Because the air is being released.
Air's going up that way?
Yeah.
Yeah.
Then it should go
Yeah.
that way. Okay, you ready? 3, 2, 1. Hold on.
Was that supposed to happen?
No.
Oh.
Trick question.
Yeah, I thought it was, for a second I thought it's a trick question. I was like,
Hold on, stand up.
Physics is a myth.
Physics was working this morning when I tried this. Okay, let's try a different balloon.
Blame the balloon.
Blame it on the balloon. It's always the balloon's fault. Hold on, I got one.
No, that was physics.
I couldn't blow up a balloon for like the longest time. I'm glad. Could you not whistle either?
No, I can't.
Oh, really? Same.
It's kind of like riding a bike.
She also. I don't know.
Catherine also can't swim.
I can't swim either.
All this is in the.
It's because we're Asian, right?
Hopefully physics works. 3, 2, 1. It kind of worked. Okay. Let's try that again. Thank you.
What if it just doesn't work ever?
He's lying to us.
Hopefully. Okay.
Let's stick to biology.
Okay, 3, 2, 1. You all got the idea.
Yeah.
Okay.
We know it should have
We know it should have happened. Now, what I'm going to do is I'm going to put a glass shield here. Okay? So we'll try this again. Now, here's the question,
What the? Wait.
Hold it.
if you would.
Okay.
Yeah, you're right. Slack out of the line. It's close now. So we'll try this again. And God knows what's going to happen with this one. We'll try this again. Now, here's the $1 million question.
What's a better angle to see?
Then we'll let go of it. Okay?
What?
Wait.
Oh, I know why.
Okay, now. So did the glass shield make any difference at all? It made no difference. It just happened to work that way.
Are you serious?
Of course, I didn't know it wanted to work that way with the blast shield because it reinforces this idea. So here's the deal. The blast shield actually makes no difference whatsoever.
What?
It doesn't.
But doesn't the air bounce off and like make it go faster?
Right? So what gives the balloon its shape?
Air.
So God, just whatever you do, don't say air molecules. I will flip out.
Air molecules?
There's no such thing as air molecules.
Carbon dioxide.
Oxygen.
So, here's the deal. So what's giving the balloon the shape? What are the particles of air doing?
They're spread out? I don't know. Wait.
Are they hitting the sides of the
Oh,
balloon?
yeah.
Yes. And then what are they doing?
And they're bouncing off
They're
and
bouncing off,
doing
right?
it.
So they're going dunk, 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 right? Okay? Oh, that's what's giving it the shape. So when I let go of it, here's the deal. So everybody says, oh, the blast shield will make a difference. So what would have to happen is all of the oxygen molecule would have to escape the back of the balloon. It would have to hit the blast shield. Then it would have to bounce off the blast shield and then turn around and hit the balloon. Okay? But here's the problem. As soon as I let go of it, which direction did the balloon go? The balloon has left the building. Okay? So the balloon isn't there anymore. So this blast shield makes no difference. All of that exchange happens is actually on the front of the balloon, because what's happening is that you still have the gas molecules hitting the front of the balloon, but you don't have them hitting the back of the balloon. So the set of equal and opposite forces happens within the front of the balloon. That blast shield had nothing to do with it whatsoever. This is why rockets can operate in space, because that set of equal and opposite forces happens within the rocket engine, because space is a vacuum. So if you had to have something for those particles to push off of, we could never fire rocket engines in space, because there would be nothing for them to push off. So the set of equal and opposite forces happens within the balloon, not with the blast shield. Unfortunately, it went the wrong way, and thank God what you did didn't go the wrong way today. So, okay, got it, good, back again. Okay. Okay. All right. So here's how we can use this idea of F equals ma. So let's say that I've got yonder fan cart, okay? And I turn it on, and I let go, and oddly enough, it begins to accelerate, right? So how could I figure out the force that's causing the cart to accelerate? F equals ma. So what would I need for the cart? I need its mass. How can I find its mass? Scale. Now, I happen to have a Newton scale. Being a physics teacher, I have those handy. Okay? So I've got a Newton scale, and I hang this thing up, and hopefully gravity still works. And I hang it up, and it weighs 4.35 newtons. So since it weighs 4.35 newtons, how can I find its mass?
Because kilograms times the acceleration of the gravity.
So this is my FG, right? FG equals mg, right?
Yes. Is that wrong?
No.
Oh, okay.
I want to get mass by itself, so what am I going to do? I'm going to divide it by 9.8 meters per second squared. Okay, because I want a mass that's in kilograms, right? Okay?
Yes.
So remember, newtons are kilograms meters per.
Second square.
So the meters squared are going to cancel out. I'm left with kilograms. So somebody take 4.35 and divide that by 9.8 meters per second squared.
No, this is mine.
0.44. Now, if I take this thing to the moon, is it going to have the exact same mass on the moon?
Yes.
Yes, because mass is a measure of stuff, okay, which is a highly impractical term, or imprecise term. So if I go to the moon, it's still going to have a mass of 0.44 kilograms, okay? Will it weigh the same on the moon?
No.
No.
No, it's going to weigh a lot less on the moon because the moon has a much weaker gravitational field, which is why the moon doesn't have an atmosphere. Okay, it just doesn't have enough gravitational pull to keep one. Earth does, that's why we have an atmosphere, which is a good thing. Mars doesn't have a strong enough gravitational field, doesn't really have an atmosphere. So, if I go to the moon, same mass, but it would weigh less, because weight is dependent upon the gravitational field. Okay, so now I've got the mass. That's the easy one. How could I determine the acceleration of the cart?
You can time it.
I could time it.
Make a little lab.
Make a little lab. Sounds like a horrible rap song. Just make a little lab. Okay, so what can I do to make a little lab?
You get the ruler and a
Well,
timer.
what are some things that I could measure?
Distance.
Oh, perhaps distance. Wow. And perhaps I could measure
Time.
Now, if I'm clever, what am I going to let the initial velocity of the cart be?
0.
0. So if I can measure distance and I can measure time, we'll make a little lab, I can figure out
The acceleration.
the acceleration. Once I get the acceleration and I know the mass, I can calculate the force.
Wow.
Wow. Okay, so let's do a little lab. Okay, so hold up. Time it. Or somebody time it. Okay, so we're going to travel exactly 1 meter. Okay. So we're going to get this up to full speed. There we go. Okay. So we're going to go 3, 2, 1, go, and then I'll tell you when to stop. Okay, you ready? 3, 2, 1, go.
Oh, it didn't start.
Okay.
Oh, it's okay, it happens sometimes.
Maybe because somebody sat here and went start and stop all day.
Wait, what?
I don't think that's the one we have.
This one's working.
Okay, you ready?
Yeah.
3, 2, 1, go. Stop. 3.65 seconds. Okay. So we did a little lab. Mary had a little lamb. Mr. Brookhamp had a little lab.
That's funny.
Okay. So so we know the distance was 1 meter. We know the time, what was the time? 3.65 seconds. What else do we know?
Distance.
Got
Oh,
that.
wait. I mean, velocity naught.
V naught is
0.
0. Okay, clever on that. And I want to calculate the acceleration. So what it relates distance, time, initial velocity.
Oh, this equation.
No.
I found the equation.
What was that?
It's not that
Not
equation.
that equation, we have time. It's this one.
Yeah, I don't want to use that equation.
It's third equation. D equals V naught time plus 1/2 AT squared. And I almost forgot.
I looked up at just the worst time, didn't I?
What happened?
Okay,
I almost forgot.
it's me and Jennifer.
Oh.
So this is going to drop out,
Checked my work and
and we're going to use this a lot. Okay, we're going to use this a lot to calculate acceleration because acceleration is really tough to measure directly. This is a handy way to do it. So to get acceleration by itself, what are you going to do?
Solve for it.
Solve for it.
times 2.
Times 2,
Wait,
Minus.
divided by T squared.
Yeah.
right?
Yeah.
Okay. So I've got 2 times 1 meter divided by 3.65 seconds squared. So what do you get?
0.274.
0.274 meters per second squared. So now we can use F equals ma, right? So we've got a mass of, what was the mass? 0.44 kilograms.
Yes.
Multiply that by, so somebody take 0.44 times 0.274 meters per second squared. What do you get? 0.12
1.
1 meters. Okay? Not a whole lot of force, right? Now, knowing this number, let's think about this. So when this fan is spinning, it can produce a force in this direction of 0.12 newtons, okay? But it weighs 4.35 newtons, okay? So if I've got this and I let go of it, will it begin to take off and accelerate upward?
No.
Why not?
Force of gravity is stronger.
Yeah, the downward force of gravity is greater than the upward force. Now, it's enough to make it move horizontally, okay? But it's not enough for me to set this thing off and go, wow, whoop, and it begins to fly upward, which would be cool, don't get me wrong. Okay, so as you go through these problems on this assignment, I want you to keep a couple of things in mind. One, every problem can only go one of two ways. What are the only two ways it can go?
Acceleration or none.
Either you're accelerating or you're at
Rest.
no, you're at
I'm
constant
sorry, I'm
velocity.
reading the wrong graph.
Now, it might be at rest, okay?
I was reading the wrong graph.
Those are your two options. Now, if you're at constant velocity, does that mean that there's no forces acting on the system? No, it just means that the sum of the forces is equal to zero. Okay, so that's option number one. So if I let this cart go long enough, it would eventually reach a constant velocity. If I let this thing go, it's not going to break the sound barrier eventually. Okay, eventually the opposing force of air resistance is going to balance out the forward force of,
Sorry.
it's okay, from the fan, right? Those would balance out. Eventually this thing would level off, you would have your velocity time graph would be producing a horizontal line. So remember, if you're at a constant velocity, the sum of the forces can equal to zero. If you're on a velocity time graph, that means that you have a horizontal line, which means that, and we'll talk more about this tomorrow, this concept of net force. A net force is what you need to make something accelerate. It's an imbalanced force. So if you have a horizontal line on a velocity time graph, you have no acceleration, and there's no imbalanced force, okay? Now, I give this thing a push, and it comes to a stop. So if it accelerates, what did the forces not add up to?
Zero.
Zero. So if you're accelerating, the sum of the forces does not equal to zero, which means now if you're going to accelerate, what are the two options when you're accelerating?
Speed up or slow down?
You are either speeding up or you are slowing down. Those are the only two games in town. You either speed up or you slow down, okay? Now, there's another way that you can have constant velocity without any forces. So imagine that we are in deep, 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 deep space, okay? And we're in deep space, no effective gravity, no air resistance, nothing. If I gave this a push towards dying, and there was no forces, there's no gravity, there's nothing. If I just gave this a push, it would go directly towards dying, because there would be no forces to make it speed up, slow down, or accelerate. So there's two ways that you can have something traveling at a constant velocity. Either there are absolutely no forces acting on it, zero, zip, none, no forces whatsoever, or there are forces acting on it, but they add up to equal to zero. Okay? Those are the only two ways that you can have constant velocity. Either no forces, or all the forces add up to equal to zero. Okay? Got that idea? Okay, so stop that camera for a second. So let me kind of go through some of these. Again, you are not answering these on the sheet of paper. You can write on it, but fundamentally, here's your sheet of paper. Draw a line, answers here, work there. Now, let me get you through number 5. Okay? No, I'm sorry, number 6. Read the wrong number 6.
That's even better.
So number 6 sounds horrible. It says, if with no friction a force F results in acceleration A when acting on a mass M, then tripling the mass and increasing the force 6-fold will result in acceleration F. Now, you're tempted to read that question and go, I'm just going to go curl up in the corner in the fetal position and suck my thumb because I have no idea how to work this problem. Okay? I'm going to show you 2 ways that you can do this, okay? A smash mouth physics approach and then an elegant approach, okay? So if you like numbers, like Burkamp, I love crunching numbers, fine. So on number 6, here's the two ways you can do this. One, you can start with the idea that force equals mass times acceleration. You can make up numbers. Numerically, what's the easiest force that you could have? That's a non-zero value.
Gravity?
1.
Oh.
What's the easiest mass you could have? 1 kilogram. What's the easiest acceleration you could have?
1.
So that's a technical definition of what 1 Newton is. A 1 Newton force, by definition, is the amount of force that it takes to take a 1 kilogram mass, like this, and make it accelerate at 1 meter per second squared. Okay, by definition, that's what that is. Now, we're going to change it based upon the new information. So instead of 1 kilogram, you're told that we're going to triple the mass. So instead of 1 kilogram, we're going to have 3 kilograms. We're going to increase the force 6-fold. So instead of 1 Newton, we're going to have 6 Newtons. So therefore, my acceleration has to be
2 meters per second.
2 meters per second squared. So what happened to the acceleration?
It doubled.
It doubled. So we went from 1 meter per second squared to 2 meters per second squared. So if you like smash mouth physics and you go, I want to, you're okay. It's like, I want to put in numbers. Fine. That is a very valid way to solve this problem. Now, here's the more elegant approach to it. Okay, this is the more elegant approach. You start with F equals ma. Now, what's going to happen to your mass? It's going to do what? Increase by a factor of 3. So instead of m, we're going to have 3m. Instead of force, we're going to have
6F.
6F. So what's the only way this will balance out?
2A.
Is if you have 2A.
Are those the answers right there?
Okay? So, I don't care how you think through the problem. It doesn't make me any difference.
Oh,
Okay?
it's a multiple choice.
Just pick one.
Yeah, the first.
Now,
Oh.
You guys are dumb.
I was like, we have to figure that out for
was
every
a
single one of
multiple
those
choice.
things.
Bro.
Oh, that makes sense.
okay. Now, when you get to number 1, okay, you're going to calculate the weight of these objects. Do not worry about making these negative. I just want the numbers, okay? All I'm asking you to do is, can you take 0.5 kilograms times 9.8 meters per second squared? Okay? That's it.
Oh dear.
Number 1? Okay. Got it.
That's the mass that's in the problem. So on number 1, I'm going to give you different masses. Okay? So 0.5, 1, 1.5, 2. Multiply them by 9.8 meters per second squared. Do not worry about making it negative. All I want you to get is the numbers. Then you're going to draw a graph with mass on the x-axis and weight on the y-axis. That actually needs to be a pretty exact graph. So if you're going to do it on your graph paper, lay it out, like space them evenly, not randomly make marks, okay? Or you can do it on graph paper. That actually has to be a pretty exact way of doing this. And then you're going to find the slope. Pay attention to the units. When you get to number 2, notice that every value I have on number 2 has 3 significant digits. All of your answers on number 2 should have 3 significant digits. Okay? When you get to number 5, okay, so here's what I want you to visualize on number 5. You're going to take a 0.5 kilogram mass and you're going to put it on a scale that measures in newtons. Okay, not kilograms, it's going to measure in newtons. So you're going to take a 0.5 kilogram mass and you're going to put it on this scale. What should the reading on the scale be?
0.5 times 9.8.
0.5 times 9.8 gets you
Your weight.
4.9.
4.9.
Okay?
Yeah.
So
Sorry.
what should happen is that scale should be reading 4.90 newtons because that's countering the gravitational pull acting on the 0.5 kilogram mass. Okay? So you got a 0.5 kilogram mass acting down. being pulled by gravity. The scale is balancing that out and providing an equal and opposite force. Okay? Now, imagine this. Then we're going to take a balloon filled with helium, and we're going to attach that to the weight. Okay? So now the balloon is going to be providing an upward force. So the balloon is providing an upward force which is trying to lift this up. Gravity is still trying to pull it down. So the gravity mafia is still acting. The gravity mafia is still trying to hold this thing down, right? The balloon is providing an upward force, okay? It's like, oh, I'm a helium balloon. I'm happy. Let's try and lift you up. And the gravity mafia is going, no, screw you, okay? We're going to keep this thing down. So what's going to happen is that, but this is going to be important, the balloon is going to be providing part of this upward force. So I tell you that once you hook up the balloon, that scale drops from 4.90 newtons to 4.80 newtons. Okay? Now, everything still has to add up to equal to 0. You have gravity pulling down at negative 4.9. The scale is providing now an upward force of 4.8. So how much upward force is being provided by the balloon? Do not make this difficult. 0.1. Why?
Oh yeah, it's 4.9.
Because everything still has to add up to
Yeah.
0, because nothing's accelerating. So gravity is still pulling down to negative 4.9. The scale is providing 4.8, because the balloon is providing the difference, which is 0.1. Keep that in mind. When you get to number 5, 5 is probably the most complicated one on the entire assignment. So imagine this. You have a box and you're pushing it along at a constant velocity. All the forces add up to 0. Okay? I gave you the coefficient of friction. That's going to allow you to calculate the frictional force. Once you know the frictional force, then you know the applied force, because everything has to add up to equal to 0 because it's moving at a constant velocity. So you're going to use mu mg, Eli. You're going to use mu mg to calculate that frictional force. So on 5a, you're going to use the Eli equation of mu mg. Okay? You know the mass, you know the gravitational acceleration, I've given you the coefficient of friction. So here's the big picture on this problem. You're pushing this thing along at a constant velocity, and then you stop pushing it. As soon as you stop pushing, what's it going to begin to do?
Slow down.
Slow down. Why? You have an imbalanced frictional force. Okay? You have an imbalanced frictional force. You're going to know what the value of that frictional force is from mu mg. Okay? That's the force that's going to make this thing slow down. Then you're going to go, oh, F equals ma. So as soon as I stop pushing it, the frictional force is going to make it slow down. You're going to know the mass. You can calculate the acceleration. So to get the acceleration, take the frictional force, because that's going to be your unbalanced force. Divide that by the mass. There's your acceleration. Okay? You're eventually going to draw a velocity time graph for this. Your velocity time graph is going to look something like this. Okay? It'll make sense when you get done with the problem. So basically, you're pushing it along at constant velocity. You're going to stop pushing it, and then it's going to slow down. So remember, when something is slowing down, that means you're accelerating. That means that you have an unbalanced force. Okay? Pay attention to everything that I want labeled on that velocity time graph. Number 6 is the easiest problem on the entire assignment. All you have to do is F equals ma. That's it. Okay? Number 6 is a gift. Don't overthink it. It's F equals ma. Now, what you're going to have to do on 7, 8, and 9, you're going to use F equals ma on 7, 8, and 9. I've given you the mass. the trick here is that you have to calculate the acceleration, okay? So that's why you have to be able to do acceleration before you do forces. So on 7, 8, and 9, the first thing you're going to have to do is calculate the acceleration and then multiply that by the mass to get the force, okay? All right, I'm done. You're on your own.